Hello again, welcome to video number 11 in magnetic fields, in which case we're going to look at electric motors, which is one of the things that you do need to know about in terms of the force on a current carrying wire, which we did the last video. And so what we need to do is just first off simplify down the motor. And we're really only going to talk about DC motors, so motors that rely on a direct current. And this is a really nice diagram of the simplistic representation of a DC motor. And it's simplistic because it's only got one coil, and the coil only consists of one loop. And when we look at DC motors in the class, we'll see that motors can have multiple coils and the loops are multiple loops as well. So here's two magnets, and they're shaped like this to make sure that the coil that's rotating on this axis here is always in a strong magnetic field. And we're using a square coil, so the only bits of the coil that are cutting the magnetic field and therefore experiencing a force, that side and that side. These sides here and here don't receive any force because they're always moving parallel to the field lines. And basically this magnet can be replaced with a horseshoe magnet, we can see various scenarios for this, and I'll show you quite a few diagrams and animation to hopefully help you understand. And here's our battery, and this here is called the commutator. And the commutator is what effectively, it comes from the term communicate, in that it communicates the current through to the coil. Because this coil is rotating, you have to have a way that the electricity can go from something that's not moving to something that's moving. And we use brushes, and these brushes are usually made out of graphite, and they push up against a ring. And for a DC motor, this ring is not a continuous ring, it's called a split ring, in that it has these two black lines here are splits in it. And that way this brush here, which is communicating with the positive end of the current, it is connected to this section of the loop, and then if we follow this around, the wire then connects to the other half, or the other part of the split ring, and then the brush presses against that, and so the current can go out. Now when this rotates, however, the halves of the split ring swap brushes that they're in contact with, so this half rotates around and then starts being in contact with that brush. And what that means, and it's sometimes hard to visualize, is that the direction in the coil, the direction the current actually goes in the coil, reverses every 120 degrees. And that's important because otherwise it wouldn't rotate. Now if we used our right hand rule for this, we would recognize, if we just looked at this piece of coil here, we're going from positive to negative, so the current is going that way in the wire. The magnetic field is going north-south, so it's going that way. And if I use my right hand rule, I would go, let me think, current that way, that way. So this wire here is experiencing a force up. And if we did the right hand rule there, this piece of the coil is experiencing a force down. So that's force magnetic, and that's force magnetic, and those two forces provide the turning force for the coil. And it's at a maximum in this position here, where the coil, if this is the coil and that's the magnetic field, where it's cutting it at 90 degrees. As the coil rotates, because it's going in circular motion, it starts cutting the magnetic field at an angle, and therefore the force is reduced. And it's reduced to a minimum when the coil comes up to the top, and that minimum section is where the brushes and the split ring come into play, so that the current direction swaps and it starts getting a push as it comes down here. And so there's a section if this is the coil, where the coil's like this, as distinct from this, there's a section here where there's no force, but it's the momentum of the coil turning that gets it over that what is effectively a dead spot. And we'll see that shortly. So let's just get rid of that writing. So that's a fairly good diagram. If you understand this diagram, you're well on the way to understanding DC motors. What's happened? So here's a more realistic view. This is actually what happens in most motors, and when we pull one apart you'll see this, but the components are exactly the same. You've still, for a DC motor, you've got a split ring, you've got your brushes, this is the positive, this is the negative, you've got your coil. In this case it's a multi-loop coil and it's wrapped around a soft metal core so that it actually is more efficient. And then you have your magnets here, and so we've got the north pole of the magnet is this one, and the south pole of the magnet this one. And so effectively that's one figure, and this is another one showing exactly the same thing, but just another diagram, and nothing's hidden in this case. Okay, so make sure you understand what they're doing. This is a multi-loop coil, or a coil that's got multiple turns. That's still one coil, and this is a single turn coil. Now, so we've got this, and again another diagram. The commutator's there, the brushes are there, the current's going there. Here this is north, this is south, so it's going to rotate a different direction. And you can use your right hand motor rule, and we would work out, in this case this is going down, this is going up, and it's going to turn around, and that produces the torque, and we can use F equals ILB to work out the force, remembering to multiply the force by 2 because you've got two sections of the coil experiencing that force. And so this is where it gets confusing, is when you're trying to visualize what's happening as it's turning. So here's one that's turning. As it turns, it hits this spot here where effectively it's a dead spot, and then because the split rings have come into play, the current reverses, but that allows the coil to keep turning in the same direction. Now this little animation shows you the direction. So what you've got to look at here is the direction. Just focus on one part of the coil as it goes round, and you'll notice that the white arrow swaps in about this position here because the split ring. So it's a combination of watching the current and what's happening with the split ring, and you'll see that the current swaps in this part of the coil to allow the arrows to keep pointing so that it rotates. And I'll talk over the top of this. Hopefully that works. Here we go. So it just swapped there. Here we go. Watch it swap. There it goes. And so this split ring is allowing the force. So you notice that the wire on this section is always got a force that pushes it to go round. If you didn't have a split ring, it would just stop like that because there would be no force being applied. Okay, making an electric motor. Will be a video on your OneNote that you can have a look at, how to make an electric motor. Here's some very simple ones. Again, the basic elements are pretty much the same. You've got your battery supplying a DC current, you've got a magnet providing a magnetic field, you've got a coil, so you've got sections that are moving and cutting those magnetic field lines. And where's the commutator, you might ask? Well, the commutator is actually on the piece of wire, probably just there and there. And what they've done here, this wire is varnished, so the varnish provides an insulator, and what you do is you strip off the varnish from one side, and so when the coil rotates enough, it is in contact, the unvarnished side of the wire is in contact with this piece of aluminium, and the current flows. Then when it rotates, you get a section of the varnish on, and the current stops flowing. So it's a very simple and it's a split ring that only has one side to it. So this is a very ineffective motor, but we'll be making these in class and you can have a closer look at them as well. And making motors has been around for ages. This is what it used to be, a battery in the old days, and people used to make their own motors, and there's going to be some videos available for you, and we're going to pull out what's called the Hudson motor kits and hopefully make a motor that works for you, a DC motor. So with an AC motor, so we've been talking about DC motors, with an AC motor, because the current is an alternating current, it changes direction for you, and so it has what's called a slip ring instead of a split ring. Remember, the DC current is always in the same direction. AC current swaps, and so you can get the motor to do its rotation with a frequency that's sympathetic to the alternating current frequency. And so here you now have what's called slip rings. And so one end of the power supply is always in contact with the same section of the coil, and the other ring is always in contact with this part of the coil. But because this is alternating, the current in the coil swaps directions, and therefore it can rotate. Now, one last thing we need to talk about before we finish this one is an instrument called galvanometers, and these are sort of like a motor. They use the motor principle, but they're used or they have been used, a bit old school now, to measure very small amounts of current because they're very, very sensitive. And why they're sensitive is because what you have, this is the basic makeup of it, you have a coil that has multiple loops in it, like hundreds of loops, and the coil is made up of very thin wire, so it has a very small amount of mass. You connect it to your circuit that's going to produce the current, so if you're testing for something that may produce current, and if a current flows in this, because there's so many, and here's a magnet as well, so if a current flows in this, these parts of the coil become a current carrying wire in a magnetic field, and they experience a force, and so this turns. And so it's a very good indicator of very, very small currents. And this is just a side-on view that's using the right-hand motor rule, and to show that how it works. And we'll pull out one of our old galvanometers and have a look at it when we're doing this. And here again the principle. They have very very well constructed magnets to maximize the magnetic field, because the wire wants to be cutting the magnetic field as consistently as possible, and usually there's a little spring to make it go back to zero. So you should be able to do question 18 now, and in the next video we're actually going to start looking at moving charges in magnetic fields. How's that sound? Cheerio!